The Sun has a visitor, and it arrived just in time for New Year's Eve. A massive sunspot designated AR4323 has rotated into Earth view, positioning itself directly facing our planet. But here's what makes this strange. This sunspot emerged in the exact location where we saw the largest sunspot of the year, the one that went dark about 2.5 weeks ago, the one everyone thought had disappeared. And now, something is back. Is this the same sunspot returning from the sun's far side, or is this something entirely new forming in the same danger zone? And why is it happening now, as the world prepares to celebrate? Stay with me. In the next few minutes, we're going to uncover the mystery of AR4323, trace its connection to December's solar giant, understand what makes a sunspot truly dangerous, and explore what this means for Earth as we cross into the new year. This is a story of cosmic timing, scientific investigation, and the delicate dance between our planet and the star we orbit. Let's begin with what we know. On December 30th, observers monitoring solar activity noticed something emerging on the Sun's eastern limb. The eastern limb is the edge of the Sun as we see it from Earth, the place where sunspots first appear as the Sun rotates. Think of it like watching something come around the corner of a spinning sphere, and what came around that corner was significant. AR4323 announced itself not with silence, but with activity. This wasn't a quiet arrival. The region was already producing flares, already showing the magnetic complexity that makes scientists pay attention. But it was the location that made everyone pause. This sunspot appeared in almost the exact latitude and longitude where AR4294 had been visible in early December. AR4294 was the largest sunspot of the entire year, a sprawling complex that captured attention when it was first spotted not from Earth, but from Mars. We'll get to that remarkable story in a moment, but first, understand the significance of this positioning. The Sun is vast. Its surface area is more than 10,000 times that of Earth. For a sunspot to appear in the same location where another massive region existed just weeks earlier isn't just unusual, it's a pattern that demands explanation. Now you might be thinking this is simply the same sunspot returning. After all, the Sun rotates. Sunspots that disappear around one edge eventually come back around the other, right? And you'd be partially correct. The Sun does rotate, taking about 27 days to complete one full rotation as seen from Earth. But here's where it gets complicated. Here's where the mystery deepens. When that same physical region returns, it doesn't always keep the same designation number. Sometimes it's given a new number entirely, and this is exactly what happened with AR4323. But we're getting ahead of ourselves. To understand what we're looking at right now, we need to understand what happened in December. We need to go back to the beginning of this story, to the emergence of AR4294, and why it mattered so much. Because without that context, you can't fully appreciate why AR4323's appearance matters, why the timing is so significant, why scientists are monitoring this so closely as we approach midnight on New Year's Eve. Here's what makes this timing so remarkable. While you're planning your New Year's Eve celebration, while millions of people around the world are preparing to count down to midnight, this sunspot is staring directly at Earth. It's in the perfect position to affect us if it decides to erupt, and it's already shown it's capable of erupting. On December 27th, an McClass flare was detected, near where this region was expected to be rotating into view. That's a medium-strength eruption, significant enough to cause radio blackouts if it had been facing Earth. It was our first warning that whatever was coming back around the Sun's edge was still active, still energetic, still dangerous. So as the clock ticks toward midnight, as people gather in Times Square and cities around the world, as fireworks are prepared and champagne is chilled, this cosmic visitor sits in perfect alignment with our planet. The Sun doesn't care about our calendars. It doesn't know we've decided December 31st marks the end of something, and January 1st marks a beginning. These are human constructs, arbitrary divisions we've imposed on the continuous flow of time. But every now and then, cosmic events align with our human timekeeping in ways that feel almost intentional, almost meaningful. And this is one of those moments. The question everyone wants answered is simple. Should we be worried? Is this sunspot going to erupt? Will it send a blast of radiation and particles toward Earth just as we're celebrating the new year? And if it does, what happens? These are reasonable questions. They deserve honest answers, and that's exactly what we're going to explore together. Not hype, not fear-mongering, just facts, context, and understanding. But to get those answers, we need to become investigators. We need to trace this story back to its beginning. We need to understand what AR4294 was, what happened during its visible period in early December, where it went when it disappeared, and what might have changed during the 2 weeks it spent on the Sun's far side. We need to understand how scientists track these regions, how they predict their behavior, and what the designation change from AR4224 to AR423 actually tells us. This is a journey that will take us from late November through December and into the final hours of the year. It's a journey that will teach you how to read solar activity, how to understand space weather forecasts, and how to put this current event into the context of a much larger cycle that our sun is going through. Because AR4323 isn't alone. It's part of something bigger, something that's been defying predictions all year, something that will continue into the new year and likely beyond. Right now, as you read this, the sun is rotating. AR4323 is moving across the solar disk, the visible face of the sun. Each hour it shifts slightly in position. Each day it travels farther from the eastern edge where it first appeared. And with each rotation, with each passing hour, scientists are watching. They're monitoring the magnetic configuration. They're analysing the likelihood of eruption. They're preparing for multiple scenarios. Because this is what modern space weather monitoring looks like. It's not guesswork. It's not astrology. It's sophisticated observation, mathematical modelling, and real-time response. And here's what makes this moment in history unique. We have the technology to watch this unfold. Previous generations would have seen sunspots appear and disappear with no understanding of what they were or what they meant. 100 years ago, we barely understood solar rotation. 150 years ago, we didn't connect solar activity to Earth effects at all, not until the Carrington event taught us that lesson the hard way. But today we can watch in real time. We can track magnetic fields. We can model eruptions. We can predict with reasonable accuracy what might happen and when. But prediction isn't certainty, and that's the tension at the heart of this story. We know AR4323 is there. We know it's active. We know it's facing Earth at a significant moment in our human calendar. What we don't know is what it will do next. Will it erupt? Will that eruption be minor or major? Will it send a coronal mass ejection toward Earth? And if it does, will our planet be in the path? Or will that cloud of plasma miss us entirely as so many do? These unknowns are what make space weather both fascinating and challenging. But they're also why stories like this matter. Because the more people understand about how our sun works, the better prepared we are as a civilization. Not prepared in a doomsday sense, prepared in a practical sense. Understanding that space weather is real, that it affects our technology, and that monitoring it is as important as monitoring hurricanes or earthquakes, or any other natural phenomenon that can impact our infrastructure. So let's continue this investigation together. Let's uncover what happened in December, what we're seeing now, and what it might mean for the days ahead. Hit that like button if you want to know what scientists are actually seeing up there, and drop a comment telling me, are you staying up for New Year's or staying up to watch the sun? Because by the time we're done, you'll understand why watching both might be the most informed way to ring in the new year. Now, to make sense of AR4323, we need to rewind the clock and revisit the solar giant that captured everyone's attention just weeks ago, the sunspot that started this entire mystery. To understand what we're looking at today, we need to go back to the beginning, back to late November, when something began forming on the sun's surface that would become the defining solar feature of the entire year. This is the story of AR4224, and it's more remarkable than you might expect. In the final days of November, a complex of sunspots began emerging on the sun's eastern limb. These weren't isolated spots. They were forming together, creating what scientists call an active region complex. The designations were AR4224, AR4296, and AR4298, all appearing in close proximity, all showing signs of magnetic complexity. But it was AR4224 that would dominate. As these regions rotated into Earth view in early December, it became clear we were looking at something significant. Around December 2nd, AR4294 had reached its peak visibility and size, and it was massive. This wasn't just another sunspot. This was the largest active region we'd seen all year. To put this in perspective, sunspots are measured in millionths of the solar hemisphere. AR4294's area reached approximately 1,000 millionths at its peak. That translates to a region several times larger than Earth itself, large enough to fit multiple Earths side by side within its boundaries, large enough to be visible to the naked eye if you used proper solar filters. Never look directly at the sun, but with appropriate protection, observers around the world could see this dark blemish on our star's face. But here's where the story gets truly fascinating. Before anyone on Earth spotted AR4294, it was seen from somewhere else entirely. NASA's Perseverance rover, sitting on the surface of Mars, conducting its mission to explore the red planet, caught sight of this sunspot complex before we did. Think about that for a moment. A rover on another planet, millions of miles away, looking back at the Sun we both orbit and seeing a sunspot before observers on Earth could detect it. This happened because of viewing angle. Mars was positioned such that it could see the Sun's eastern limb before Earth's rotation brought that region into our view. It's one of those moments that reminds you we're not just observing the cosmos anymore, we're observing from multiple points within it. When AR4294 did rotate into Earth view, scientists immediately began comparing it to historical records. How significant was this sunspot? Where did it rank? And the comparisons that emerged were sobering. While AR4294 wasn't the largest sunspot ever recorded, it was being compared to regions associated with major solar events. The Carrington event of 1859, the most powerful geomagnetic storm in recorded history, was caused by a sunspot complex. And while we don't have precise measurements from that era, estimates based on historical observations suggest AR4294 was in a similar size class. That comparison sparked conversations about potential impacts. If a sunspot this large produced a massive eruption directed at Earth, what would happen? Would our modern infrastructure survive? These are questions we'll explore more deeply later, but they were very much on people's minds as AR4294 made its way across the solar disk throughout early December. Now here's what surprised many observers. Despite its size, despite its magnetic complexity, AR4294 remained relatively quiet during its Earth-facing period. It produced flares, yes. There were C-class eruptions, minor events that barely registered on Earth, but the catastrophic X-class flare that its size suggested was possible never materialized. Day after day, astronomers watched, space weather forecasters issued outlooks, and the sunspot remained active but not explosive. It was like watching a sleeping giant. Powerful, impressive, but not threatening, at least not yet. This relative calm doesn't mean the sunspot was insignificant, far from it. The magnetic complexity was there. The energy storage was evident. Sunspots don't need to erupt to be important. They're manifestations of the Sun's magnetic field, and studying them teaches us about the processes happening beneath the visible surface. Scientists use this period to analyze AR4294's structure, to model its magnetic configuration, to understand why this region had grown so large and what that meant for solar cycle predictions. Every sunspot is a data point, and a sunspot of this magnitude is a treasure trove of information. But all sunspots have a limited time in the spotlight. The Sun rotates, and what faces Earth today will face away 2 weeks later. Around December 12th and 13th, AR4294 rotated around the Sun's western limb. It disappeared from Earth view, beginning its journey across the Sun's far side. And this is where the story enters its mystery phase. Because once a sunspot goes around that corner, we lose direct observation. We can't see it anymore. It's hidden, travelling across the hemisphere of the Sun that faces away from Earth. For the next 2 weeks, AR4294 was in the dark, at least from our perspective. And during those 2 weeks, anything could have happened. The region could have grown. It could have shrunk. It could have split into multiple regions or merged with new emerging flux. Sunspots are dynamic. They evolve constantly. And without eyes on the region, we had to wait and wonder what version of AR4294 would emerge on the other side. But scientists weren't entirely blind during this period. There are tools that allow limited observation of the Sun's far side. Spacecraft positioned at different points in Earth's orbit can sometimes glimpse regions we can't see directly. Helioseismic analysis, which studies sound waves moving through the Sun, can detect large active regions even when they're not visible. And then there are the indirect signs. When a sunspot erupts on the far side, we can sometimes detect the eruption itself, even if we can't see the source. And this is exactly what happened on December 27th. Monitoring equipment detected an MAC-class flare. The signature was clear. Somewhere on the Sun's far side, an active region had erupted with medium-strength force, and the timing suggested it was coming from the location where AR4294 should have been. This was the first hint that whatever was travelling across the far side was still active, still energetic, still worth watching when it came back around. Russian scientists were among the first to announce the expected return. On December 26th, space weather monitoring services in Russia issued alerts that AR4294 would be rotating back into Earth view within days. They predicted the region would reappear on the eastern limb around December the 30th or 31st. They were right. But what appeared wasn't designated AR4294 anymore. It had a new name, a new number, a new official designation. It was now AR4323, and that changes where our investigation takes its next turn, where we have to understand how sunspot numbering actually works and why this region received a new identity. That's a story of scientific systems, naming conventions, and the challenge of tracking features on a constantly changing star, and it's where we're headed next. When AR4224 disappeared around the Sun's western limb in mid-December, it entered a phase that might be called the hidden chapter. For about 2.5 weeks, this massive active region travelled across the hemisphere of the Sun that faces away from Earth. And during that time, we lost our primary view of what was happening. This dark side journey is one of the most intriguing aspects of tracking solar activity, and it's worth understanding both the challenges it presents and the tools scientists use to maintain some level of awareness even when direct observation isn't possible. First, let's establish exactly what happens when a sunspot rotates out of view. The Sun rotates on its axis, just like Earth does. But unlike Earth, the Sun doesn't rotate as a solid body. It's a ball of plasma, and different latitudes rotate at different speeds. The equatorial regions rotate faster than the polar regions, completing a rotation in about 25 days. Higher latitudes take closer to 35 days. From Earth's perspective, which is orbiting the Sun while the Sun is also rotating, the average rotation period we observe is about 27 days. This means a sunspot that disappears on one side should reappear on the other side roughly 2 weeks later. But during those 2 weeks of transit across the far side, the sunspot isn't frozen in time. It continues to evolve. Magnetic fields continue to interact. The convective processes beneath the Sun's surface continue to pump energy into the region or drain it away. A sunspot can grow significantly during this hidden period. It can also decay. It can split into multiple regions. It can merge with newly emerging active areas. All of this happens out of sight, which means when the region rotates back into view, it might look very different from when it disappeared. This uncertainty is a fundamental challenge in space weather forecasting. Imagine being a meteorologist who could only see half the Earth at any given time. You're tracking a storm system as it moves across the visible hemisphere, but then it crosses into the zone you can't observe. 2 weeks later it emerges on the other side. Has it strengthened, weakened, changed direction, split into multiple storms? You're working with predictions based on models, but you won't know for sure until it comes back into view. Solar scientists face this same challenge, but they're not completely helpless. There are several techniques that provide glimpses of the far side. One method is helioseismology, which studies sound waves travelling through the Sun's interior. These waves are affected by magnetic fields, and large active regions create distinctive signatures that can be detected even when the region is on the far side. It's like using sonar to detect something you can't see directly. The resolution isn't perfect, but it can confirm whether a large active region still exists and approximately where it's located. Another tool is spacecraft positioned at different points in the solar system. For years, NASA's stereo spacecraft provided views from angles ahead of and behind Earth in our orbit. This allowed scientists to see portions of the Sun that weren't visible from Earth. While the current stereo missions have limitations, other spacecraft like the Solar Orbiter, a joint European Space Agency and NASA mission, occasionally provide different viewing perspectives. These glimpses aren't continuous, but they're valuable data points. Then there are the indirect observations. When a sunspot erupts with a powerful flare or coronal mass ejection, that event can be detected even if we can't see the source. Solar flares emit X-rays and extreme ultraviolet radiation that can be measured by satellites. Coronal mass ejections, the massive clouds of plasma hurled into space, can be observed by coronagraphs, instruments that block the Sun's bright disk to see the fainter corona. If an eruption happens on the far side, we might see the effects, even if we can't see the cause. And this is exactly what happened on December 27th. Multiple monitoring systems detected an McClass flare. The classification was M5.1, a solid medium-strength eruption. The timing and characteristics suggested it originated from the region where AR4224 should have been during its far-side transit. This was significant for several reasons. First, it confirmed the region was still active. It hadn't decayed into nothing during its time out of view. Second, it demonstrated the region still had enough magnetic complexity and energy storage to produce significant flares. And third, it served as a warning. If the region could produce an McClass flare while on the far side, it could certainly do so once it rotated back to face Earth. Russian space weather monitoring services were tracking this carefully. On December 26th, they issued alerts noting that the former AR4224 region would be rotating back into Earth view within days. They predicted the reappearance would occur around December 30th or 31st, right at the cusp of the new year. These predictions were based on solar rotation calculations, tracking where the region had been when it disappeared and projecting where it would reappear. But here's what nobody could predict with certainty. What state would the region be in when it came back? The M5.1 flare suggested ongoing activity, but had the region grown or shrunk? Had its magnetic configuration become more or less complex? Was it more dangerous than when it left, or less? These questions could only be answered by direct observation, which meant waiting for the region to rotate into view. As December 30th approached, solar observers around the world turned their attention to the Sun's eastern limb. This is the edge where new features appear, rotating into view from the far side. And right on schedule, something began to emerge. A sunspot complex started appearing exactly where predictions said the former AR4323 should return. But when the official designation was announced, it wasn't AR4224 anymore. It was AR4323, a new number, a new identity, and to anyone not familiar with how sunspot numbering works, a source of confusion. Why the designation change? This is a critical question, and the answer tells us a lot about how scientists track solar features and what the new number actually means. It's not a conspiracy. It's not an attempt to hide anything. It's a systematic approach to cataloguing evolving solar regions. But to understand it, we need to dive into the details of how NOAA's Space Weather Prediction Center numbers active regions, and that's our next destination in this investigation. Because understanding the designation mystery is essential to understanding what AR4323 really is, and whether it poses any greater or lesser threat than the AR4294 we watched in early December. The numbering system holds the key to decoding what changed during that 2-week journey across the Sun's hidden hemisphere. Now we arrive at the heart of the confusion, the question that sparks debate in every space weather forum and social media thread when an event like this occurs. If AR4323 appeared in the same location where AR4294 was, if it emerged right on schedule when the old region should have rotated back into view, then why does it have a different number? Is this a new sunspot, or is it the same one returning? And what does that designation change actually tell us about what might have happened during the farside journey? Let's start by understanding how sunspot numbering actually works. The system used today is maintained by NOAA's Space Weather Prediction Center. When a new group of sunspots appears on the Sun and meets certain criteria for size and magnetic complexity, it's assigned an active region number. These numbers are sequential and continuous. They started decades ago and have been counting upward ever since. The current number sequence is in the 4000s because we've been systematically numbering solar active regions for that long. Here's the key principle. These numbers are assigned to active regions when they appear on the Earth-facing side of the Sun. When a region rotates out of view around the western limb, it keeps its number while it's on the far side, at least conceptually. But here's where it gets interesting. When that same physical location rotates back into view 2 weeks later, scientists have to make a decision. Does the returning region get to keep its old number, or does it receive a new one? The answer depends on what happened during the farside transit. If the region has evolved significantly, if its structure has changed substantially, if it's merged with new emerging flux or split into different components, then it's considered a new active region and receives a new number. This isn't arbitrary. It reflects the reality that sunspots are dynamic features. They're not permanent marks on the Sun. They're temporary manifestations of magnetic field interactions, and those interactions don't pause just because we can't see them. Think of it this way. Imagine tracking a river during flood season. You observe a particular configuration of water flow, eddies and rapids at one location. Then you lose visibility of that section for 2 weeks. When you can see it again, the water is still flowing in roughly the same area, but the specific patterns have changed. The eddies have shifted, new rapids have formed, old ones have smoothed out. Is it the same river? Yes, in terms of geographic location and source. But is it the same flow pattern? No, it's evolved. The designation change reflects this evolution. So when AR4323 appeared on December 30th, what NOAA was saying is this. Yes, there's an active region appearing in the location where AR4224 was. Yes, it's almost certainly the same magnetic source region, but it has evolved enough during its farside transit that it warrants a new designation. The structure we're seeing now isn't identical to what we saw in early December. Something changed. Now let's look at what specifically changed. When AR4294 rotated out of view in mid-December, it had an area approaching 1,500 millionths of the solar hemisphere. It was the largest active region of the year. When AR4323 rotated into view, its area was smaller. Still significant, still noteworthy, but not the sprawling giant we'd seen before. This suggests some decay happened during the farside transit. The region lost area. It became more compact. But area isn't the only factor that matters. What really determines a sunspot's threat level is its magnetic complexity, and this is where the classification system comes into play. Sunspots are categorized based on their magnetic configuration. The classifications range from simple to complex, using letters and combinations that describe the magnetic structure. The simplest type is called alpha, a single spot with a simple magnetic field. More complex types include beta, where there are positive and negative magnetic poles present, like a magnet with north and south. Then there's beta gamma, where the field is more intertwined. And the most complex is beta gamma delta, where the positive and negative polarities are so intertwined within the same penumbra, the outer region of a sunspot, that the energy storage and release potential is highest. AR4323 was classified as type EKC, which indicates a complex configuration with multiple spots. The magnetic analysis showed it still possessed complexity, still had the potential to store significant energy and release it through flares. In fact, the M5.1 flare it produced on December 27th, before it even came fully into view, demonstrated this capability, so while the region might have lost area, it hadn't lost its teeth. It was still magnetically complex enough to be taken seriously. This is where understanding the designation change becomes important for threat assessment. Some people see the new number and think it's a completely different sunspot, unrelated to AR4224. Others see the location match and assume it's exactly the same region, with identical characteristics. The truth is in the middle. It's the same magnetic source region, the same location on the Sun, but it's evolved, it's changed, and those changes mean we can't simply copy-paste our assessment from early December. We have to evaluate AR4323 on its own current characteristics. What this also tells us is that the Sun is more dynamic than many people realize. We talk about sunspots as if they're solid objects, but they're not. They're regions of intense magnetic field penetrating through the Sun's surface. Beneath that surface, in the convection zone where hot plasma churns and circulates, magnetic fields are constantly being generated, twisted, and reconfigured. What we see as a sunspot is just the surface expression of processes happening below, and those processes continue whether we're watching or not. During AR4294's far-side journey, those subsurface dynamics continued. Plasma continued to flow, magnetic fields continued to interact. Some of the field may have emerged through the surface in new configurations, some may have submerged. The region we call AR4323 is the result of those 2 weeks of hidden evolution. It's related to AR4294, the way a child is related to an adult version of themselves. Same source, different stage, different configuration. Now, does this make AR4323 more or less dangerous than AR4294 was? That's not a simple question to answer. The smaller area suggests less total magnetic flux, which could mean less energy storage. But the continued complexity and the demonstrated ability to produce McClass flares mean it's still a region worth monitoring. Space weather forecasters are watching it carefully, analyzing its magnetic configuration in real time, and updating threat assessments based on current observations. What we can say with confidence is this: AR4323 is the returning manifestation of the magnetic region we knew as AR4294. It's evolved during its time out of view. It's smaller in area but still complex, it's active, as proven by the December 27th flare, and most importantly it's facing Earth during a symbolically significant time in our human calendar. Even though the Sun doesn't care about our New Year's Eve celebrations, the designation change isn't hiding anything. It's accurately reflecting the dynamic nature of solar active regions. If you want to track this region's history, you trace it back to AR4294. If you want to assess current threat levels, you look at AR4323's present characteristics. Both designations are correct for their respective contexts, and understanding this system helps us communicate more clearly about what's happening on the Sun and what it might mean for Earth. So now we know what we're looking at. We know AR4323 is the evolved version of December's solar giant. We know it's still complex and active, but what does that actually mean? What makes a sunspot dangerous in the first place? What are we really watching for when we monitor these regions? To answer those questions, we need to dive into the physics of how sunspots work, why they erupt, and what happens when they do. That's the education portion of this journey, and it's essential for understanding why this particular sunspot matters and what consequences its activity could have for Earth. Let's explore the science behind the threat. To understand what we're really watching when we monitor AR4323, we need to understand what sunspots are at a fundamental level. They're not just dark blemishes on the Sun's surface. They're not scars or shadows. They're magnetic phenomena, and everything about their behavior, their danger level, and their impact on Earth comes down to magnetic fields and energy. Let's start with the basics. The Sun is a ball of plasma, which is essentially ionized gas where electrons have been stripped from atoms by intense heat. This plasma is constantly in motion. The Sun's interior is like a boiling pot, with hot plasma rising from the core, cooling at the surface and sinking back down in convective cycles. This motion generates magnetic fields through a process called the dynamo effect. Moving charged particles create magnetic fields, and the Sun's complex internal motion creates incredibly powerful magnetic fields that thread throughout its interior and surface. Sunspots form when these magnetic fields become so intense in a particular region that they pierce through the Sun's surface. The magnetic field is so strong that it inhibits the normal convective flow of hot plasma from below. This means the sunspot region doesn't receive as much hot material rising to replenish it. As a result, that area becomes cooler than its surroundings, and cooler plasma emits less light, which is why sunspots appear dark. They're not actually dark in an absolute sense, they're still incredibly bright, thousands of degrees hot, radiating intense light. But compared to the surrounding photosphere, which is even hotter and brighter, they look dark by contrast. But temperature and appearance are just surface manifestations. What really matters is the magnetic field structure, and this is where complexity comes into play. Some sunspots have relatively simple magnetic configurations. Imagine a single loop of magnetic field emerging from the Sun's interior, with one end being a north magnetic pole and the other end being a south magnetic pole. This creates a simple sunspot pair, and while they're impressive to observe, they're relatively stable. But when multiple magnetic field loops emerge in close proximity, when they twist around each other, when positive and negative polarities become intertwined within the same region, that's when things get dangerous. This is like taking multiple rubber bands and twisting them together tightly. You're storing energy, and that energy wants to be released. In the Sun's case, that release happens through a process called magnetic reconnection. Magnetic reconnection is one of the most important processes in solar physics, and it's worth understanding even if the details get a bit technical. When magnetic field lines with opposite polarities come into close contact, they can break and reconnect in a new configuration that has lower energy. The difference in energy has to go somewhere, and it goes into accelerating particles and heating plasma to extreme temperatures. This is what we see as a solar flare, a sudden bright flash of radiation across the electromagnetic spectrum. Solar flares are classified by their X-ray intensity into categories. C-class flares are the weakest significant category, minor events that barely affect Earth. Mac-class flares are medium strength, capable of causing brief radio blackouts on the sunlit side of Earth and minor radiation storms. X-class flares are the major events, powerful enough to cause widespread radio blackouts, significant radiation storms, and if they're directed at Earth, serious impacts on satellite operations and communications. But flares are only part of the story. Often accompanying a flare, especially the larger ones, is a coronal mass ejection. This is a different phenomenon with different consequences. While a flare is a radiation event that reaches Earth at the speed of light within minutes, a coronal mass ejection is a physical cloud of plasma, billions of tons of material hurled into space by the explosive release of magnetic energy. This material travels much slower, typically taking 1 to 3 days to reach Earth if it's aimed in our direction. When a coronal mass ejection impacts Earth, it doesn't hit our surface directly. We're protected by Earth's magnetic field, which acts as a shield. But the interaction between the incoming solar plasma and Earth's magnetosphere can cause geomagnetic storms. These storms can induce electrical currents in power grids, potentially causing blackouts. They can disrupt GPS signals. They can damage satellites. And on the positive side, they create auroras, the beautiful light displays seen near polar regions, and sometimes at lower latitudes during intense storms. So when we talk about a sunspot being dangerous, what we're really talking about is its potential to produce powerful flares and Earth-directed coronal mass ejections. And that potential is directly related to the magnetic complexity of the region. This is why scientists spend so much time analysing sunspot magnetic configurations. They're not just classifying them for academic interest, they're assessing threat levels. AR4323's classification as a complex region with multiple spots means it has stored magnetic energy. The fact that it produced an M5.1 flare on December 27th proves it can release that energy. The question is whether it will produce something larger, and whether any eruption will be directed at Earth. This is where the current geometry comes into play. A sunspot can erupt at any time during its life cycle, but the impact on Earth depends entirely on where the sunspot is located on the solar disk when it erupts. If it's near the center of the disk as we see it, an eruption is more likely to head directly toward Earth. If it's near the edge, the eruption will likely be aimed off to the side. AR4323 appeared on the eastern limb, which means it started at the edge of the visible disk. As the sun rotates, it's moving toward the center. The next several days represent the window when an eruption would have the highest probability of being Earth-directed. And this is why the timing matters. This is why scientists are paying attention. Not because there's certainty of eruption, but because the geometry is aligning such that if an eruption occurs, we're in the firing line. It's like standing in a field during storm season. The presence of storm clouds doesn't guarantee lightning will strike you, but it's prudent to be aware of the risk and have plans in place. Now let's talk about what actually happens when Earth is impacted. Your modern life depends on technology that's vulnerable to space weather. Satellites in orbit provide GPS navigation. They relay communications, they monitor weather, climate, and military activities. A powerful radiation storm from an X-class flare can damage solar panels and electronic components on satellites. Enough damage can render them inoperable. GPS signals can be disrupted or degraded for hours or days. Radio communications, especially high-frequency radio used by aviation and maritime operations, can be blacked out on the sunlit side of Earth during a flare. This is because the X-rays from the flare ionize the upper atmosphere more than usual, and these ionized layers absorb radio waves instead of reflecting them. Pilots and ships rely on these communications, so space weather warnings are issued to give them time to switch to alternative communication methods. Power grids are vulnerable to geomagnetic storms caused by coronal mass ejections. When Earth's magnetic field is disturbed by incoming solar plasma, it creates fluctuating magnetic fields around our planet. These fluctuating fields induce electrical currents in long conductors, and power lines are perfect long conductors. The induced currents can damage transformers, the critical infrastructure components that are expensive and time-consuming to replace. In extreme cases, this can lead to widespread blackouts. This isn't theoretical, it has happened. In March of 1989, a geomagnetic storm caused a power blackout in Quebec, leaving millions without electricity for hours. That storm was caused by a coronal mass ejection from an active region much like AR4323. And there's evidence of even more powerful events in the past, like the Carrington event of 1859, which we'll discuss more later. The point is, space weather has real consequences for our technological civilization. But here's what's important to understand. We're not defenseless. Modern space weather monitoring is sophisticated. We have satellites watching the sun continuously. We can detect flares within seconds of their occurrence. We can observe coronal mass ejections as they leave the sun and track their trajectory. We have models that predict arrival time at Earth. And we have protocols in place. Power grid operators can take protective measures. Satellite operators can put spacecraft into safe modes. Airlines can reroute flights around polar regions where radiation exposure is higher during storms. This is why sunspots like AR4323 matter. Not because they're doomsday threats, but because they're risks that need to be managed. And management requires awareness. It requires monitoring. It requires understanding the science so we can assess the threat realistically, neither panicking nor ignoring it. So as AR4323 continues its journey across the solar disk, scientists are watching its magnetic evolution. They're analyzing the likelihood of flares, they're preparing forecasts for the days ahead. And this brings us to the current situation, the space weather conditions right now, as we approach New Year's Eve. What's the forecast? What's actually happening? What should people expect? Let's look at the real-time situation and what it means for the next several days. Right now, as December 30th transitions into December 31st, as the world prepares for New Year's Eve celebrations, space weather is active. Not catastrophically so, but active enough that forecasters are paying close attention. Let's break down what's happening in real time, what the forecasts are showing, and what you might actually experience if you're in the right place at the right time. The current space weather forecast shows geomagnetic storm conditions. On December 30th, a G2 moderate geomagnetic storm is underway. This is being caused primarily by high-speed solar winds streaming from coronal holes, which are areas of open magnetic field on the sun that act like cosmic fire hoses, sending streams of solar wind toward Earth. These coronal hole streams have been quite active throughout late December, contributing to several rounds of aurora activity at high latitudes. By December 31st, New Year's Eve itself, the forecast shows conditions moderating slightly to G1 minor geomagnetic storm levels. This is still elevated above quiet conditions, but it's a step down from the 30th. What this means in practical terms is that aurora activity is expected, particularly at high latitudes. If you're in northern regions like Canada, Alaska, Scandinavia, Iceland, or northern Russia, your chances of seeing auroras are quite good. The lights might dance across the sky as you count down to midnight, a natural fireworks display courtesy of the sun. But here's where AR4323 enters the picture. The current storm conditions are primarily from coronal holes, not from sunspot eruptions. AR4323 hasn't produced any major flares since rotating into Earth view, at least not yet. But the presence of this active region adds an element of uncertainty to the forecast. If AR4323 produces a significant flare and coronal mass ejection while it's facing Earth, that could enhance the geomagnetic storm activity or trigger new storms in the days that follow. Space weather forecasters describe this as a watch situation. Not a warning, which would indicate an event is imminent or already occurring, but a watch, which means conditions are favourable for something to happen. AR4323 has the magnetic complexity to produce M-class or potentially X-class flares. Its position is rotating toward the centre of the solar disk, meaning any eruptions over the next several days have a good chance of being Earth-directed. But whether it will actually erupt, and if so, when and how powerfully, that's something we won't know until it happens. This uncertainty is fundamental to space weather forecasting. Unlike weather on Earth, where we have centuries of data and sophisticated models that can predict conditions days in advance with reasonable accuracy, space weather is more challenging. We understand the physics of what makes sunspots erupt, but we can't predict the exact timing. It's like knowing that a particular storm system has the potential to spawn tornadoes, but not knowing exactly when or where they'll touch down. So what should you expect over the next few days? Let's break it down by impact category. First, auroras. If you're at high latitudes, particularly in northern regions, you have a good chance of seeing aurora activity even without any contribution from AR4323. The existing geomagnetic storm conditions from coronal holes are sufficient to produce displays. If AR4323 does erupt with an Earth-directed coronal mass ejection, and if that eruption is powerful enough, it could enhance aurora visibility and push the aurora zone southward. During strong geomagnetic storms, auroras have been visible as far south as mid-latitude states in the United States and equivalent latitudes in Europe and Asia. Whether that happens depends entirely on whether AR4323 cooperates. For aurora hunters, the key is to monitor space weather forecasts in real time. Services like NOAA's Space Weather Prediction Center, spaceweather.com, and various aurora forecast apps provide up-to-date information on geomagnetic activity levels and aurora visibility predictions. If you're in a location with clear skies and low light pollution, and the forecast shows elevated activity, it's worth stepping outside after dark to look north. Auroras are most commonly visible in the hours around midnight and into the early morning. Second, radio communications. If AR4323 produces a significant flare, particularly in M-class or X-class flare, while it's facing Earth, there will be a radio blackout on the sunlit side of the planet. This affects high-frequency radio communications used by aviation, maritime operations, and amateur radio operators. Commercial aviation has protocols for dealing with these blackouts, including switching to satellite communications when HF radio is unavailable. For most people, you won't notice this impact directly unless you're operating an aircraft or ship or are an amateur radio enthusiast. Third, satellite operations. Radiation storms associated with powerful flares can affect satellites in orbit. Satellite operators are aware of the current conditions and are monitoring for any increased risk. Most satellites have procedures for safing their systems during radiation storms, which might mean temporary interruptions in certain services. GPS accuracy can degrade during geomagnetic storms due to ionospheric disturbances. Again, for most civilian users, this is unlikely to be noticeable, but high-precision applications might experience reduced accuracy. Fourth, power grid concerns. This is where the conversation sometimes veers into alarmism, so let's be clear about the actual risk. For AR4323 to cause power grid issues, several things would need to happen. It would need to produce a very powerful X-class flare with an associated coronal mass ejection. That CME would need to be directed squarely at Earth. It would need to have the right magnetic orientation to efficiently couple with Earth's magnetic field, and even then the impact would depend on power grid preparedness and response. Modern power grid operators are aware of space weather risks and have protocols in place. The likelihood of AR4323 causing widespread power blackouts on New Year's Eve or in the days immediately following is low. Not zero, but low. The more likely scenario is that AR4323 will produce some level of flare activity, possibly M-class flares that cause radio blackouts and minor geomagnetic disturbances, but nothing approaching the catastrophic end of the scale. This is based on statistical analysis of sunspot behavior. While complex regions can produce powerful flares, The majority of active regions go through their Earth-facing period without producing the kind of extreme event that makes headlines. But probability isn't certainty, and this is why monitoring continues. Space weather forecasters update their assessments multiple times per day based on the latest observations. If AR4323's magnetic configuration shows signs of increasing instability, if emerging flux is adding complexity, if the region begins showing precursor activity that often presages major flares, the forecasts will be updated accordingly. For the average person, the most likely positive outcome of this entire situation is an enhanced chance to see auroras over the next several nights. If you've ever wanted to witness the northern lights, this might be your opportunity. The current geomagnetic activity provides a baseline, and any contribution from AR4323 could make displays even more spectacular. There's something poetic about potentially seeing auroras on New Year's Eve, a reminder that while we're celebrating a human calendar milestone, the cosmos continues its ancient dance regardless of our timekeeping. And this brings us to a larger question. How worried should we actually be? What's the realistic threat level? To answer that, we need to put AR4323 into historical context, to compare current conditions with past events, and to honestly assess the vulnerability of our modern technological infrastructure. That's not about fear-mongering, it's about informed awareness. So let's examine the infrastructure question directly and see what history teaches us about solar storms and their impacts on human civilization. Let's address the question that lingers beneath every discussion of major sunspots and potential solar storms. Should we be worried? Is our modern infrastructure truly vulnerable to space weather events? And if so, what's being done to protect it? These are legitimate concerns, and they deserve honest, detailed answers, free from both doomsday alarmism and dismissive hand-waving. To understand current vulnerability, we need historical context. The benchmark event for extreme space weather is the Carrington event of September 1859. This was the most powerful geomagnetic storm in recorded history, and it occurred at a time when human technology was far more primitive than today. The world had telegraph lines, which were the cutting-edge communication technology of the era. During the storm, telegraph systems across North America and Europe experienced severe disruptions. Operators received electrical shocks. Telegraph paper caught fire. Some systems continued to work even after being disconnected from their power supplies, running on the electrical currents induced by the disturbed magnetic field alone. But here's what makes the Carrington event particularly significant. It wasn't just the infrastructure impact, which was limited because there was so little infrastructure to impact. It was the Aurora observations. During this storm, auroras were visible as far south as the Caribbean, Hawaii, and Colombia near the equator. People in these tropical locations saw curtains of red and green light dancing across the sky, phenomena normally confined to polar regions. This tells us something about the intensity of the magnetic disturbance. For auroras to be visible at equatorial latitudes, the geomagnetic storm must have been extraordinarily powerful. Modern analysis of the Carrington event, using ice core data that preserves records of solar particle impacts and other proxy measurements, suggests the flare that caused it was likely X-class, possibly in the range of X40 or higher on the current classification scale. For context, the most powerful flare measured in the modern satellite era was X28 in November 2003. The Carrington flare may have been significantly more powerful. Now, what would happen if a Carrington-class event occurred today? This is where things get sobering. Our technological infrastructure is vastly more complex and far more vulnerable than telegraph wires. We have power grids spanning continents, with high-voltage transmission lines stretching thousands of miles. We have satellites providing GPS, communications, weather monitoring, and military capabilities. We have undersea fiber optic cables carrying internet traffic. We have pipelines monitored and controlled by electronic systems. All of this could potentially be affected by an extreme geomagnetic storm. The scenarios have been modelled. In 2008, the National Academy of Sciences published a report examining the potential impacts of severe space weather events on modern infrastructure. The findings were concerning. A Carrington-level event today could cause widespread power grid failures lasting weeks or months in affected regions. Transformers, the critical high-voltage components that take years to manufacture and replace, could be damaged beyond repair. Satellite communications could be severely disrupted. GPS systems could become unreliable or non-functional. The economic cost was estimated potentially in the trillions of dollars. These aren't science fiction scenarios. They're based on engineering analysis of how infrastructure responds to induced electrical currents and radiation. And we have a more recent near-miss to consider. In July 2012, the Sun erupted with a Carrington-class coronal mass ejection. Fortunately for Earth, it was aimed in a different direction. The CME tore through the orbit where Earth had been just 1 week earlier. If the timing had been different, if that eruption had occurred 7 days later when Earth was in the firing line, we would have experienced a direct hit. So yes, the threat is real, but before anyone panics, let's talk about the other side of the equation, which is preparedness and resilience. We're not in 1859 anymore. We're not helpless. We have early warning systems. We have spacecraft monitoring the sun continuously. When a major flare occurs, we know about it within minutes. When a coronal mass ejection is launched toward Earth, we can track it, model its trajectory, and predict its arrival time, typically 1 to 3 days later. This warning time is critical. Power grid operators can take protective measures. They can reduce loading on the grid. They can prepare to isolate vulnerable sections. They can delay maintenance that would leave parts of the grid more vulnerable. Satellite operators can put spacecraft into safe modes, turning off non-essential systems and orienting solar panels to minimize radiation exposure. Airlines can reroute flights to avoid polar regions where radiation exposure is highest during solar particle storms. These mitigation measures don't eliminate risk, but they significantly reduce it. Moreover, there's ongoing work to harden infrastructure against space weather. Power grid operators in many countries have implemented space weather monitoring and response protocols. Satellite designs increasingly incorporate radiation-hardened components. New transformer designs are being developed that are more resistant to geomagnetically induced currents. It's a slow process, and the level of preparedness varies significantly by country and region, but progress is being made. The question of AR4323 specifically needs to be framed within this larger context. Is AR4323 likely to produce a Carrington-class event? Based on current observations, no. While it's a significant active region with demonstrated flare potential, it's not showing the extreme characteristics that would suggest an imminent superstorm. The M5.1 flare it produced is notable, but nowhere near the top end of the scale. Could it produce an X-class flare? Possibly. Complex sunspots can surprise us, but even X-class flares vary enormously in strength, from X1 to X20 and beyond. Most X-class flares, while serious, don't cause catastrophic impacts. What AR4323 represents is the normal operation of an active sun during solar maximum. We're in the peak phase of solar cycle 25. Powerful sunspots are expected. Significant flares are normal. Geomagnetic storms happen regularly. This is part of the sun's natural rhythm, and while individual events can be disruptive, they're manageable within the framework of modern space weather monitoring and response. But the larger conversation that AR4323 has sparked is valuable. It reminds us that space weather is a real component of our planetary environment. It's not something we can ignore just because it seems exotic or distant from everyday concerns. Our technological civilization is built on infrastructure that's vulnerable to these events, and continued investment in monitoring, forecasting, and mitigation is essential. This is similar to earthquake preparedness in seismically active regions, or hurricane preparedness in coastal areas. The existence of the threat doesn't mean abandoning the location. It means building with the threat in mind, having warning systems and preparing response protocols. Space weather is no different. We can't prevent solar eruptions, but we can observe them, predict their impacts, and take measures to protect critical infrastructure. So as AR4323 continues across the solar disk, as we move through New Year's Eve and into early January, the appropriate response is informed awareness, not fear, not dismissal, awareness. Recognition that this is a significant active region worth monitoring, that space weather can have real impacts, and that systems are in place to manage those impacts. For most people, the most direct effect will be the potential to see auroras, which is an opportunity to witness one of nature's most beautiful phenomena. For operators of critical infrastructure, it's a reminder to stay vigilant and follow space weather forecasts. And this event, AR4323's emergence right at year's end, provides an opportunity to step back and look at the bigger picture of what's happening with our sun. Because this isn't an isolated occurrence. It's part of a larger pattern, a solar cycle, that's been surprising scientists and exceeding predictions. Understanding that cycle, understanding where we are in it and where we're going, that's essential context for making sense of events like AR4323. So let's zoom out and look at solar cycle 25 itself, at why it's been so interesting, and at what we can expect in the year ahead. To fully understand AR4323 and why its appearance matters, we need to zoom out from this individual active region and look at the larger cycle it's part of. The sun operates on an 11-year rhythm, a cycle of magnetic activity that goes from quiet periods called solar minimum to active periods called solar maximum and back again. We're currently in solar cycle 25 and it's been full of surprises. Let's start with how solar cycles work. The sun's magnetic field isn't static. It's generated by the complex motions of plasma inside the sun, particularly in the convection zone where hot material rises and cooler material sinks in massive circulation patterns. This internal motion creates magnetic fields through the dynamo process. Over time, these fields become twisted and tangled. Eventually, they become so distorted that the magnetic field essentially flips, with the north magnetic pole becoming south and vice versa. This happens approximately every 11 years, and the period from one minimum to the next is called a solar cycle. During solar minimum, the sun's surface is relatively quiet. Sunspots are rare, flares are infrequent. The sun's magnetic field is more ordered, but as the cycle progresses toward maximum, activity increases. More sunspots appear, flares become more common. The sun's magnetic field becomes increasingly complex and tangled. At solar maximum, the peak of the cycle, the sun's surface is dotted with active regions and significant solar events occur regularly. Then the cycle begins its decline back toward minimum. We've been tracking these cycles systematically since the mid-18th century, numbering them sequentially. Solar cycle 25 began in December 2019. That was solar minimum, the quiet period between cycles. From there, activity was expected to gradually increase toward a maximum, predicted to occur sometime in 2025. But here's where things got interesting. The predictions for solar cycle 25 suggested it would be relatively weak, similar to the previous cycle. Solar cycle 24 was one of the weakest on record, with lower sunspot numbers and less overall activity than many previous cycles. Scientists expected cycle 25 to follow a similar pattern. The forecast showed a modest maximum with peak activity well below the historical average. Reality has not cooperated with those forecasts. Solar cycle 25 has been significantly more active than predicted. Sunspot numbers have exceeded predictions month after month. The frequency of X-class flares has been higher than expected, and the timing of the maximum appears to be arriving earlier than the original forecast suggested. Some solar physicists now believe we may already be at or very near the peak of the cycle, rather than still approaching it. December 2025 was a perfect example of this unexpected vigor. The month saw significantly elevated solar activity compared to previous months. Multiple active regions appeared, including the AR4223 complex that dominated early December. The number of significant flares increased, and as we've seen, AR4323 represents the continuation of this active period right into the end of the year. Why has cycle 25 been stronger than predicted? That's a question solar physicists are actively investigating. It might relate to how we model the sun's internal dynamo. It might involve interactions between different layers of solar plasma that we don't fully understand. It could be natural variability that our models don't capture. The sun is not a simple system, and predicting its behavior is challenging despite our sophisticated understanding of solar physics. What this means for the year ahead is significant. If we're at or near solar maximum now, we can expect continued high activity throughout much of 2026. Sunspots like AR4323 won't be anomalies. They'll be regular features of the solar landscape. Geomagnetic storms will occur frequently, Aurora activity will remain elevated, and space weather will continue to be a factor that satellite operators, power grid managers, and aviation authorities need to monitor closely. But there's another possibility worth considering. Some solar cycles have what's called a double peak, where activity rises to a maximum, declines somewhat, and then rises again to a second peak before the final decline towards solar minimum. If cycle 25 follows this pattern, we might see a period of relative quiet in the coming months, followed by renewed activity later in 2026 or into 2027. It's too early to know for certain, but the historical precedent exists. What we can say with confidence is that the sun remains in a highly active state. The conditions that produced AR4293 and now AR4323 are ongoing. The magnetic complexity that allows these powerful active regions to form is present throughout the sun's interior, and as long as we're in the solar maximum phase, we should expect more significant sunspots to appear. This isn't cause for alarm. Solar maximum is a normal part of the sun's cycle. We've been through many of them before, but it is cause for continued attention. Each solar cycle teaches us more about how our star works. Each significant active region provides data for improving our models and forecasts, and each space weather event helps us refine our understanding of how solar activity affects Earth and our technological infrastructure. For space weather enthusiasts, this is an exciting time. The next year will likely provide numerous opportunities to observe solar phenomena, from sunspots visible through safe solar filters to auroras visible at high and sometimes mid-latitudes. For scientists, it's a rich data environment for advancing our understanding of solar physics, and for society, it's a period that demonstrates why space weather monitoring and preparedness matter. AR4323 is one chapter in this ongoing story. It appeared at a symbolically significant moment in our calendar, right at the transition from one year to the next, but it's part of a much longer narrative of solar activity. When we look back on 2025, it will be remembered as a year when the Sun exceeded expectations, when solar cycle 25 proved more vigorous than predicted, and when multiple significant active regions reminded us that space weather is a real and present factor in our technological age. As we move into 2026, we carry forward the lessons of this year. We know the Sun is active, we know significant events are possible, we know our infrastructure is vulnerable but not defenseless, and we know that continued observation, continued research, and continued investment in space weather capability is essential for a civilization that depends increasingly on space-based technology and interconnected power grids. AR4323 will eventually rotate out of view, just as AR4294 did. It will make its own journey across the Sun's far side, and we may or may not see it return. But whether this particular active region produces major eruptions or fades quietly, it's part of a larger pattern. The Sun's activity will continue, new active regions will appear, and the dance between our planet and our star will go on, as it has for billions of years. What's changed is our ability to watch, to understand, and to prepare. That's the real story here. Not the fear of a single sunspot, but the ongoing effort to comprehend the star we orbit and to build a civilization that's resilient in the face of its inevitable variability. Now, as we bring this investigation to a close, let's step back and take a cosmic perspective on what we've learned and what it means. Here we are, at the end of a year, at the cusp of a new one, and the Sun has delivered a reminder that our planet exists within a dynamic system, that the star we orbit isn't a static ball of light, but a churning cauldron of plasma and magnetic fields. That our technological civilization, for all its sophistication, is still vulnerable to forces beyond our control. And yet, there's something beautiful about this moment, something that puts our human concerns into perspective while simultaneously making them feel more connected to the universe we inhabit. AR4323 appeared on December the 30th. New Year's Eve falls on December 31st. This timing is, from the Sun's perspective, completely meaningless. The Sun doesn't operate on human calendars. It doesn't know we've divided time into years, months, and days. It doesn't care that billions of people will gather tomorrow night to celebrate an arbitrary boundary between one trip around our orbit and the next. The Sun follows rhythms measured in millions and billions of years, cycles of magnetic activity that operate on their own schedule. And yet here we are, marking our human milestone while this cosmic event unfolds. There's a kind of poetry in that. As fireworks explode over cities tomorrow night, as champagne glasses clink and countdown clocks reach zero, the Sun will continue its rotation, AR4323 will continue its journey across the solar disk, and the magnetic forces that might produce the next flare will continue building or releasing according to physics that preceded humanity, and will continue long after we're gone. This perspective doesn't diminish human experience. If anything, it enriches it. We're part of something larger. Our planet is connected to its star by more than just gravity and light. We're bathed constantly in the solar wind, that stream of particles flowing outward from the Sun's corona. Earth's magnetic field protects us from most of this radiation, creating a protective bubble in space. But when the Sun erupts, when active regions like AR4323 release their stored energy, we feel the effects. Auroras dance in our skies, our satellites experience interference, our power grids respond to induced currents. We are, quite literally, touched by the Sun, and we've learned to watch. This is what makes this era unique in human history. For millennia, people saw sunspots appear and had no framework for understanding them. Ancient Chinese astronomers recorded sunspot observations 2,000 years ago, but they couldn't explain what they were seeing. In the 1700s, observers noted that sunspots appeared and disappeared in patterns, but they didn't understand the connection to magnetic cycles. It wasn't until the 1800s that we began to connect solar activity to Earth effects, and that connection was forced upon us by events like the Carrington storm. Now, in the early 21st century, we have spacecraft watching the Sun continuously from multiple angles. We have instruments that can measure magnetic fields on the solar surface. We can observe in wavelengths of light invisible to human eyes, seeing the Sun's corona, its atmosphere, its eruptions in exquisite detail. We can track sunspots from emergence to decay. We can model the complex physics that drives their behavior, and we can predict with improving accuracy what effects their activity will have on Earth. This knowledge is empowering. It allows us to prepare. It enables us to build resilient infrastructure. It turns space weather from an invisible mystery into a manageable challenge, but it also gives us something less tangible, and perhaps more important. It gives us connection. Understanding that AR4323 is not just a dark spot but a magnetic structure millions of miles across. Understanding that its potential eruptions are releases of energy that could fill millions of hydrogen bombs. Understanding that we can see the effects of these distant events in our own skies. This understanding creates a sense of participation in the cosmos. You are living on a planet that orbits a magnetically active star during its maximum activity phase. You're experiencing right now the effects of solar cycle 25. When you look at auroras, you're seeing the visible manifestation of your planet's magnetic field interacting with plasma from the sun. When your GPS signal degrades during a geomagnetic storm, you're experiencing the consequences of ionospheric disturbance caused by solar particles. You're not separate from these events. You're part of them. And AR4323, whether it erupts spectacularly or fades quietly, has served a purpose beyond its physical effects. It's sparked conversations. It's made people look up, metaphorically and literally. It's reminded us that space weather is real. It's created an opportunity for learning, for understanding, for appreciating the complex dance between Earth and Sun that makes our existence possible. So what happens next? AR4323 will continue its trek across the solar disk. Over the next several days, it will move from the eastern limb toward the center. If it maintains its magnetic complexity, scientists will continue monitoring it closely. If it produces significant flares, space weather forecasters will issue warnings and predictions for Earth impacts, and eventually, probably within a week or two, it will rotate around the western limb and disappear from view, beginning its own far-side journey. Will it return? Will we see AR4323 come back around in mid-January with yet another designation? Maybe. Or maybe the magnetic structure will have decayed by then, the active region dissolving back into the sun's chaotic magnetic field. Either way, it will have been one chapter in the ongoing story of our sun's activity, and you now have the tools to follow that story. You understand what sunspot designations mean. You know why numbers change. You can read space weather forecasts and understand what G1 or G2 or higher geomagnetic storm levels indicate. You know the difference between a flare and a coronal mass ejection. You understand why magnetic complexity matters. You've seen how solar rotation brings active regions into and out of Earth view. This knowledge doesn't make you a solar physicist, but it makes you an informed observer. Resources for continued observation are readily available. NOAA's Space Weather Prediction Center provides daily forecasts and real-time data. Spaceweather.com offers accessible explanations of current activity with excellent images. NASA's Solar Dynamics Observatory provides stunning real-time images of the sun in multiple wavelengths. Amateur astronomers with properly filtered telescopes share sunspot observations. Aurora forecast services tell you when and where lights might be visible. All of this information is free and accessible. So as you celebrate New Year's Eve tomorrow night, as you reflect on the year past and the year ahead, take a moment to think about the sun. Think about AR4323 facing Earth at this precise moment. Think about the possibility that auroras might dance in the sky while you're counting down to midnight. Think about the fact that you live in an era when we can watch our star in real time, when we can predict its effects, when we can prepare for its variability. And if you're so inclined, step outside after dark and look toward the north. If you're at high latitudes and the forecast is favorable, you might see the auroras. You might see the tangible evidence of space weather, the visible connection between Earth and Sun. And if you don't see them, that's okay too. Just knowing they're happening somewhere, knowing that the sun's energy is interacting with Earth's magnetic field right now, knowing that you understand the process even if you can't see it directly, that knowledge itself is valuable. The universe is vast and often incomprehensible, but moments like this, when a sunspot appears at a symbolic time in our human calendar, when we can watch and understand and prepare, these moments make the universe feel a little less distant. They remind us we're not separate observers of cosmic events. We're participants. We're affected by them, and, increasingly, we're able to respond to them. AR4323 is just one sunspot. But it's also a window into understanding our place in the solar system. It's a reminder that space weather matters. And it's an invitation to stay curious, to keep learning, to keep watching the sky. Because the sun will continue surprising us. Solar cycle 25 will continue unfolding, and there will be more moments like this. More opportunities to witness the dynamic nature of our star, and to appreciate the delicate technology, dependent civilization we've built in its light. Thank you for taking this journey through the mystery of AR4323. If you found this valuable, subscribe for more deep dives into space weather and solar phenomena. Drop a comment below telling me if you've ever seen auroras or if you'll be watching for them this New Year's Eve. Share this with anyone who might be curious about what's happening on the sun right now. And most importantly, stay curious. Keep looking up. The universe has so much to teach us. And we're living in an era when we can actually understand what we're seeing. That's a gift, and it's one we should never take for granted.